Okay, perfect. So welcome everybody to the inaugural Transboundary Groundwater Resiliency Research, which we call TGRR Network Seminar Series. This is a bi-monthly series that provides perspectives from leading global researchers on how system science and data science can contribute to transformative water research. And the series is co-hosted with the System Dynamics Society's Water Special Interest Group. So for anybody unfamiliar, TGRR is a National Science Foundation funded international network of networks that connects hydrology, social science, data science, and systems science to establish a novel transboundary groundwater resiliency research approach. If you're not already part of our network, welcome. And we encourage you to sign up for our mailing list and also to complete a survey to officially join TGRR and to join our Slack channel to just continue the conversation and connect with colleagues. We also have a volunteer leadership opportunity series available for students and early career researchers, which you can apply for on our website. And we're going to drop the links to everything I just mentioned in the chat so that you can access it later today. We're really honored to have Dr. Anna Mijic present today as our inaugural speaker. Her presentation is going to be followed by about 20 minutes of Q&A. So you can either drop your questions in the chat at any point, and we'll be keeping track of those throughout the presentation, or you can ask your question directly during the Q&A session. And so with that, I'm going to turn it over to TGRR Principal Investigator, Dr. Sam Fernald.
Thanks, Ashley. And I just got back from sabbatical in London. One of the greatest things that happened over there was I connected with the group at Imperial College London, and Dr. Anna Mijic is the director of the Center for Systems Engineering and Innovation at Imperial College London, and a reader in water systems integration. She leads the development of novel systems tools focused on quantifying interactions between water systems and sustainable development, and now is also leading Ventura. It's a project that brings together interdisciplinary expertise across water management, systems engineering, computer and geoscience, digital technology, innovation, social science. She's a systems analyst lead for the Camellia Impact Program, where her work focuses on developing systems water management models. And we just had a great discussion yesterday about kind of swapping systems and system dynamics models. I'm so excited to have Anna here, and please take it away.
Thank you, Sam, and thanks so much for for having me. I'm going to share my screen now, and what I've chosen for today is the selection of the work that we do, which is linked to the just to find the right one. Yep, this one. So selection of the work that we do around this, what we call systems water management, and I'll try to explain what we mean by that. The title is rather long, but what fundamentally I would like to communicate with this one, and the kind of takeaway message from the seminar, is the need of integration. And I think I don't need to persuade you too much about that. I think what is maybe more important is to talk about how, and we'll hopefully cover that in the next half an hour or so. So this is just to set the scene. Again, we don't need to discuss this in any great detail. Challenges that we face include climate crisis, but of course, maybe or equally importantly, environmental degradation on one side. And then on the other side, we do have the role of infrastructure. And my background is in civil engineering and water engineering. So I do have to, and I want to think about very strongly about the water infrastructure as a way of enabling the quality of life that we have, but also now infrastructure being very tightly connected with the environment, there is possibly new role of infrastructure in managing the natural environment in a different way than we did before. And with that in mind, what is also really important is not only how we design the infrastructure, but equally how we use the infrastructure, how we operate the infrastructure, and what is the information that we use to make our decisions. So with that in mind, what I will focus today is answering three questions, key or just questions. So the first one is on the vision. So how we envision the future built natural, so very tightly connected systems. Coming back to the evidence, how we evaluate the performance, and then how we are thinking about redesigning them in the context of the vision that we have and future change. And then finally, how do we integrate decisions on how to regulate, operate, design, and build for the future using systems approaches. So let's unpack one by one. So the first one is on the vision. And again, as I mentioned at the beginning, the way how we see, and I know your group sees it in a very similar way, is that human natural systems and human water systems are inherently completely joined up infrastructure projects, which are designed to work, or should be designed to work with the environment. And when I started thinking about that from the policy perspective, I spent 1 year working very closely with the UK Environment Agency. UK Environment Agency is responsible for the implementation of the environmental regulation. This is the report that was published as a result of that collaboration. And what we were looking in there is at the very high, or the highest level of conceptualization, how we can see water management from the systems perspective, with the aim to really understand why we are struggling to solve quite a few of water management problems. So what was the main output from that work is what we call systems water management meta model. And meta model means that it's not a real model in a sense of simulation, but it's more a way of thinking about a system which would help us understand what do we need to measure or simulate. So when I started kind of looking into what that meta model should be, I have started with a basic element in the UK 25-year environment plan, which says that the purpose of the plan is to have the environmental or the catchment state in a good state, not just now, but also for the future generations. So that notion around the environmental state is in the essence. Again, we can discuss what we mean by this, the good state. But then fundamentally, why that is important is because if we have functioning environment, that it provides a range of ecosystem services, and they are or should be beneficial for our quality of life. So this is, so for those who work on the natural capital, for example, evaluation, this is, you know, kind of way of how we would try to evaluate the value of our natural systems. But then what is actually happening is that how the system works in practice is that the quality of life is normally measured by the economic indicators, that our level of development is quite intensive from the perspective of resources. And then this loop, because it's driven by the economics rather than the state of the environment, is what in system theory is called the reinforcing loop. So the better we live, the more resources we need, the more resources we need, the more we build, the better we live, and it goes into a loop. But then again, of course, this resources intensive way of life does create a footprint, and that footprint fundamentally has the negative impact of the environment. And we have multiple examples of that, anything from the resources use, discharges, pollution, and so on. And if this meta model is true, and if it would function perfectly, then we wouldn't actually have a problem, because if in any signal in the decrease of quality of life because of the environmental degradation, we would change our resources dependence loop. So we would change the way how we use our resources, we would be fine because we would rebalance the system automatically. But of course, that doesn't happen. So in the most simple way of thinking about why it doesn't happen, we could argue that the infrastructure has a very important role here, and a very interesting role So infrastructure here, so what this meta model says is that the resources or the demand supply balance is managed by the infrastructure. But then that infrastructure, in order for this to be a positive loop, so we want this to be a positive loop to counterbalance the negative loop around the environmental capacity, infrastructure here needs to have a positive effect. And this is something that we really need to think about very strongly, how we design systems, infrastructure systems that don't have the negative impact on the environment, or in some way balance of this. So this is our meta model, and the hypothesis is if the system is designed in such a way, it would or it should enable development, which is represented with this loop, and then balancing the footprint and infrastructure which supports development. What is maybe interesting here, and I think this comes to the point around the collaborative decisions, is that the premise of this meta model is that any change in any component of this meta model really needs to induce the change in other models. So if we decide to develop, so this is, for example, here, then all the other aspects of this meta model need to be checked, the decisions need to be propagated, and everyone needs to react to that. What is, of course, very difficult in the UK, but I don't think this is the case only for the UK, that responsibilities for these different components come within completely different, well, I guess organizations or part of the society. So quality of life, I mean, one can argue we are all responsible for quality of life, but I guess at the kind of organizational level, it's the government that is responsible. And then for different elements of the development, we have different ministries. So in UK, for the development, we have the Ministry of Housing. In local communities, we have Department for Business, Energy and Industry, Industrial Strategy. Then, especially for the environmental state, we have DEFRA, which is Department for Environment, Food and Rural Affairs. And then if we think about the infrastructure, so water systems are private in the UK. So there is a range of water companies, there are 10 water companies, and they are regulated by Ofwat, which is, Ofwat is the government regulator which sets the water price. And then we have these two components, which basically, well, fundamentally are the way how physical processes work, isn't it? And then how we make our decisions. So very kind of strong, again, element in the system. So if this is the case, and what happens in the UK, of course, is that the regulation for all of these is done separately, that the implementation is done separately, and then even within the single system, such as water infrastructure, decisions are made separately on the water supply and the wastewater systems, they're separately from the urban and rural systems and so on. So lack of that integration is really, I would argue, huge challenge and the reason why we are struggling to achieve our fundamental goal, and that is the good state of the environment. So how we use this meta model is to do some mapping. So these are all qualitative, or this one that I will show you, there are more examples in the report if you want to have a look. So we have been asked how to implement this meta model and to look specifically at the impacts of the lake water quality in the north of England. So it's a Windermere Lake. It's a very popular lake which has huge problems with the algae bloom. And they wanted to know what are the range of interventions they can think about in these systems to manage the lake water quality. So the details are, you can have a look at the details, but what is fundamentally interesting is that if you use the meta model to try to map the system, even in this relatively simplified representation, you will always find the elements of all the subsystems that we mentioned. So this is the pollution bit. So this is the problem that they wanted to look at. And of course, there are elements of the catchment that are interesting for us. It's surface water, groundwater, rainfall, land use, and so on. And again, the quality of life, which is really important component for us to understand the value of the environment. In this case, quality of life is really important from the perspective of using the lake for the tourism. So a lot of local economy is dependent on the good quality of the lake because it provides lots of income for people who live there. And then, of course, we have the elements that are, again, existing in any regional system. We have urban water, we have agriculture, and the pollution coming from both of those. And then we have other economic sectors. So we have our development, which again, will have transport and housing in most regions. There is a local production as well, and there's also a strong emphasis on tourism is a really important sector here. And what I mentioned at the beginning when I introduced the case study, that the really important part of direct kind of information link between the catchment state and the quality of life are the direct environmental services on using the lake for the recreational purposes. So again, of course, in each of these technical subsystems, we have the element of the use and the behavior. And how we use this is to then now, if we have this high level mapping, we thought, okay, now we can look not only at the technical interventions within the system, but we can also look at the range of interventions across different components of the system. And what you see here, so this is the lake water quality. You see those interventions mapped in these numbered boxes. And then also what we did with this so this is the range of literature where this information came from. But also what we did here is to rank those interventions using Donella Meadows' leverage point hierarchy, which is very, very interesting to me, especially because, she argues that any physical interventions, so any infrastructure interventions, such as new standards, buffering capacity, changing system structure, and so on, are those that actually have the lowest impact at the systems level, because unless they're implemented across the system, so if you upgrade your adding new elements to increase the capacity, or you're upgrading maybe your wastewater treatment plant, unless it's implemented on all the treatment plants that have the direct link with the water quality, you haven't fundamentally solved the problem. And you also, of course, haven't solved the problem of all the pressures that will keep increasing the pressure on the wastewater treatment and so on. And then again, of course, if we go up that scale, the more we go into informational leverage points, the more we go into the policy and regulation, of course, then the influence of those will propagate across the system as a whole, and we have better chances to solve the problem fundamentally. Of course, having in mind that we need to think about if any of those interventions would have some unintended consequences. But a lot of material for, if nothing else, a discussion between the different stakeholders and thinking about which of these options, again, these are just proposed options. Implementation, of course, is a completely different story. Okay, so this is on the qualitative side. So the other thing, of course, in an ideal scenario, we would like to have also the quantitative evidence around the system and how what works best, at least in the things that we can simulate. So with that in mind, we have started a couple of years, we have started working on what we call the WSI mod, or Water Systems Integration Modeling Framework. The idea behind that is to try to come up with the minimum viable definition of the components so that we can integrate as many as possible elements of the water system. And how the framework looks like at the moment, so it's under constant development. What is behind the framework is a database of the range of, for now, only publicly available information in the UK. And you see the range of information here. Environment Agency has lots of public data around the flow and some public data around the water quality. Office for National Statistics, the census data, population data, National Real Flow Archive is on the flow, British Geological Survey, so lots of land use information and so on. So we, when I say we, my team, they have collected those data, processed those data, and they are preparing those data. So we now use them manually. We are preparing all of those data to be automatically pre-processed to feed into the model. And again, this is the pre-processing, so a range of algorithms that are using those data to create conceptualization for the model, input data, and also we can also use them as a calibration parameters as we do when we are comparing the results. And then how the framework works is that we have developed components for different elements of the water system. And again, these are the guiding principle for us. So they have the physical representation and again, medium customization in a sense. Each of these components could be relatively simple or it could be more complex, and I'll show you the example of that. But the components range from infrastructure components such as reservoir, treatment plants, but then also the components around the land use and also the natural components. So we simulate also rivers, groundwater, and so on. And also we add the behavior. So we also simulate the demand and the decisions, and we can also add the policy. So it's a really water management model. How then once we have the components, so components are like Lego blocks, you can pick and choose what do you want to simulate. Everything from household up to the regional scale. And then what the user needs to do is to define give the rules for the integration. And for that integration, we use the push-pull principle. So what we need to tell the model is how the two components talk between each other. Okay, so if we have river reservoir link, of course, we'll take the water from the rivers, but we'll also discharge. There may be a spill from the reservoir. And then the final bit, which is maybe most unique for the model, is that the orchestration of the model. So the way in which all of these rules are executed is completely it has to be completely customized. What that enables us is to really build the model which is specific. So you can make a model for a very specific water systems. You can add any regulation, any rule basically, which gives us a lot of flexibility to represent different types of interventions in the system. Okay, and then just in maybe last 15 minutes, I'll give you just a few examples of those models, some of the published work, some of the work in preparation. So what we started with is with a city watt model. So it's the model at the city scale. You see now the components and how these components are linked, and you should, everyone will recognize the urban water system, taking the water from the river and groundwater, using that water, and then discharging it back to the wastewater system. In this example, we are modeling the infrastructure. We are taking river and groundwater as a boundary condition, and we're using the observed data here, but I'll show you, well, I won't show you the results, but we now have the model that does the simulates catchment and groundwater as well. And we simulate London as lumped. So we see London as kind of one big node with the upstream abstractions, downstream discharge. And we simulate both flow and the water quality, which is, again, also important if we want to think about the integrated perspective. And these simulations are the daily simulations for quite a long period. And so when we did that, we first thought, okay, we need to find some way to check if the model performs. And we used two information to validate the model. So upstream, we compared the results from the simulation of our model, so green is CityWatt, with two water resources models, both which are used by the water company. So Thames Water is the water company. So this is the lumped volumes around the supply reservoirs. And as you will see, considering the simplicity of the model, the agreement was even for us surprisingly good. And then we also compared the results downstream. So I mentioned that the UK Environment Agency has a range of point samples, but again, some sampled water quality data. So this is the example for phosphorus. And again, apart from two measurements, we were doing extremely well on the water quality side. And for us, this was very pleasing result, but also something that gave us some confidence that the way how we think about it might work. And then we start playing with the model, which is really nice thing. If you have those integrated models, we can start looking at things which are not normally connected in the modeling, at least in the infrastructure modeling, and seeing, what are the benefits, what is the added value of such a model. In this case, we looked what is the added value if we can look at the water supply. So this is water supply and the wastewater system. So link between the abstraction and discharges, of course, through the river flow. And one scenario that we looked at is in the usual, in a kind of default operational mode, we have some abstractions, then, there is a river, there are some discharges, and the mixture between the upstream flow and what is coming from the treatment plant will define the percentage of the untreated effluent. And say in this case, it's 50%. But then we also looked at the combination of parameters and how they correlate with respect to this percentage of the untreated effluent. And the dots in red are the combination of the days when the precipitation is higher than 10 millimeters, but also the reservoir is full. Okay, so the reservoir is almost at its full capacity. And what we were thinking then, okay, can we set a new rule to say if the precipitation is higher than 10 millimeters and the reservoir is 99% full, leave more water in the river, okay? So abstract less, slightly less. But what now, of course, happens then is that you leave more water in the river and you increase dilution, okay? So that we can get from, something which was higher to something that is lower just by changing the operational rules. So we tried that. And then the question was, well, is it significant? So we checked if it's significant. So what you see here is the phosphorus concentration without the option. Abstraction option is called abstraction effluent dilution. That's AED stands for. So this is without, this is with, and you see here, especially for the high values of the phosphorus, you see the significant, you see the decrease in the concentrations. And then my postdoc, Dr. Barney Dobson, then did the calculations around how the sizing on the infrastructure that would need to be designed to have the same effect. And of course, the investment, and the numbers are quite significant. So you could think about this as a saving for the water company because they are improving the water quality with change on the operational rules. And of course, we did check the, what happens on the water supply side. And basically, during this period of simulations, only 6 days are new days that the system goes in the lowest level of restrictions compared to simulations without the option. And then the other thing that the models like this can really help us is to do integrated planning, because now not only looking at the interaction between the supply and wastewater, we can also change any component of the system and see how the change propagates. And we can look at the range of intervention, and you see them here, starting with the land management, rainwater harvesting, demand management, leakage management, and more complex options such as wastewater reuse. So this is this arrow here, and seeing how they they perform in this arrangement. So how we presented those results is by a relative change. So the graph here shows the relative change between the simulation baseline and the simulation with all of the individual options. And green means better, so the indicators improve. And if they're not, like here, there may be some that are, relatively nothing much changes. And this one is the only one actually that was a negative, and I'll explain why. And then again, from the perspective of integration, what is important that we look at the range of supply options, the range of wastewater options across a range of indicators, which are again relevant for the supply, but also relevant for the environment and the wastewater side. And then, of course, what you can do with this, if we're thinking about the cost-benefit analysis, you can really capture all the benefits or core benefits across the system. And we see options such as demand reduction doing, of course, really well on both sides, because this is your driver. This is kind of relatively high in that in the system's representation. But this one is really interesting because the wastewater reuse, so diverting water back into the supply, which is one of the schemes that is proposed in the UK, actually does have a negative impact on the untreated effluent as a proportion of the river flow. And the reason for that is, of course, that wastewater, although it's not a perfect water quality, it does provide water that is part of the flow that has the role in dilution. So something, not to say we shouldn't do wastewater reuse, because obviously it has lots of benefits, but something that needs to be checked. So potential unintended consequence if that aspect is not taken into account. And then we also, the next step we did, we said, okay, this is the lump scale. Can we do better than that? Here is where we looked at the same model, but just instead of having London as a lump, we divided London in how many? Nine wastewater zones. So these color-coded areas. And we also looked at the change of the water quality along the river. So what you see here, a different sampling point and a range of water quality indicators that has been collected by the UK Environment Agency. And we see as we go from upstream to downstream, so there is a change in water quality as we go along Thames. But here we look at the very specific kind of scenario. We said, okay, if we can model London in the kind of more detailed way, and you see here the kind of how that looks from the conceptual perspective, and then we also have the separate and the combined sewer. What we were really interested in is the impact of COVID-19 restrictions on the water system. And in order to understand that, we had to build more detailed demand generator. And this is what I mentioned, that each of the components could have relatively simple or more detailed module behind that. Here we went Barney added the calculations of water demand based on the individual appliances, but also based on the commuter flows. And why we wanted this is because the biggest change during COVID, isn't it, was the restriction on the movement. So we wanted to understand what's the normal restrictions, and then we imposed some rules. So what the result of that is that we developed demand use profiles on 3 scenarios. Lockdown is basically people not going anywhere. Working from home is a kind of less strict lockdown profile. And then the third one is assumption that, some of the population, because of all of these restrictions, will actually move out of London. And you see here how those profiles, so this is a daily consumption profile, change under those scenarios. And what we did then, of course, is just put it back through the model to see what are the implications. And these are the results. So again, here, what you can see is the kind of similar representation of results, which is the baseline, the scenario against baseline for the flow and the range of water quality indicators. We could look at what is happening at the household level for each of the wastewater zones. And we see some interesting things here, such as slight increase in consumption in some boroughs or wastewater zones, because just people having more time to perform water consuming activities. One thing that I should mention, of course, this is Central London. Most people work here. So we also see that significant changes in the Central London. So this is Beckton area because of the reduction of the use of the toilets. So quite interesting, I guess, for us, information that we have seen. And then, of course, we can also look what is happening all the way downstream, so how that impacts the river water quality. So it's the same range of information, but just now at the basically for each of the wastewater zone, for each of the not each, but selected water quality stations in the rivers, both Thames, but also two of the tributaries. So this is Lee, this is River Lee, and this is River Wandle, so tributaries of Thames. And again, we see some interesting things, such as that the pollutants that we see that they change at the household level are not always the same, and usually not the same as those that change in the rivers, because of the different chemicals which naturally occur or don't occur in the rivers, and then any change in the human water use does completely affect them. And then something that is maybe even more interesting is, of course, something that kind of was expected, but these results really show and make it very kind of significant, is that, of course, the tributaries are much more sensitive to any changes in the water use, of course, because smaller rivers have they have smaller dilution capacity, and of course, because people were spending more time in the suburban areas, we see changes in the water quality profile. And again, why is this important? And we did discuss these results with Thames Water, is that any changes in the inflow, of course, of the flow of the wastewater in the quantity and quality does affect or could affect their wastewater treatment works. And then I will finish with this. We talked about the integration and especially the kind of aspect of the regulation. And one of the uses of the models like this is to now just run the model with the future scenarios. And this is exactly what we did. So this is the lumped London model that you've seen at the beginning. We use the climate scenarios because again, the model runs river and groundwater are the observed data. So we run the model with the projected flows. And then what we can see here is the range, range of scenarios to capture, of course, the uncertainty in a future projections. So this is the cumulative density function. And we have chosen again the treated effluent concentration as the proxy for water quality. And we see again, so you see, so green is the baseline, blue is the near future, this is red is the far future. And again, we see kind of two interesting things here. But we see that as we go more into the future, we see increased concentration of the effluent. So the risk or the probability of the concentration increases as we go into, so if we compare green, blue, and red. But then again, we see this change in the data here. So all of these concentrations, so if we go from, I don't know, 0.45% of the treated effluent, we see that anything above that, the risk of or the probability of occurrence is very low, okay? So why is that the case? Is because the abstractions in the UK are regulated by the abstraction licenses, and we see we see, you know, them nicely functioning here in this change of the data. But then again, if we plot the same results separated by the level of restriction, so the depending on the amount of water in the river, water companies would need to go into 4 levels of restrictions. And again, 1 is the lowest level, 4 is the most strict level of restrictions. So if we plot those results with the current regulation, we see some very interesting result. And the interesting result is that the water quality at which the regulation starts to become functional is, so basically that the water quality in the restrictions 1 and 4 is lower and well, almost 5% lower than water quality in the restrictions level 2 and 3, okay? Bearing in mind that water quality is in the restriction 4 is the most severe one, okay? So then when we saw these results, so we thought, okay, if you're allowing the deterioration of the water quality for the restrictions 2 and 3, I mean, why don't we release the basically the restrictions for the level 4 as well? So basically make it more gradually increasing. And if we do this, so if we just change the alternative regulation for the obstructions, allowing, so you see here that the water quality overall is not worse than the worst scenario here. We of course allow more water to be taken out. And again, thinking about the impact, basically such change of the rule would provide water companies additional 110 megaliters per day, which is at the same level of water quality which is currently observed or predicted by the model for the level 2 restrictions. So that would be all from me. This is I have shown you a lot of urban simulations. We do have also the models that do catchment scale or integrated urban and catchment scale, which may be a talk for some other occasion. But just to summarize the presentation, we did talk about, or we started talking about the interconnectedness or integration. And you know, it's easy to say that everything is connected, but it is, at least it should be from the decisions perspective. And if we have the capability to look at that, then we can really think about how the infrastructure, isn't it, works for the environment, the link that I've mentioned here. And again, having those models, I would argue, does help us, because it at least gives us a tool to test a range of different scenarios where we can either see some unanticipated benefits, or we can look at the different designs of different policies. And again, the resolution is always a big question. We talk about that a lot. What's the minimum scale that we should be doing this kind of modeling, and does it make sense? But again, we can play with the scale, but we can also play with the detail around the representation, different components. And again, where we see the ultimate aim is to ultimately really do keep that state of our environment good, not just for us, but also for the future generations. So that is all from me. Thank you for listening. And I have to mention my team. So I just talk, they do the work. Dr. Barney Dobson, Duncan Graham, who is now a PhD student at the ETH Zurich, and then my 2 PhD students, Liang Liu and Pepe Pouchot, who are doing amazing work. So thank you all very much.
So that was absolutely a wonderful systems perspective. Thank you ever so much. I have some questions, but I'd like to open it up to the audience first and see whatever questions or comments they might have for you.
I think there are some questions in the chat. I don't know if we want to maybe
Sam, you're on mute.
Yeah, I'm clicking mute, but it's not unmuting. The first question I see is about the slides, and
Yeah, no,
Ashley,
I
will
can
this be
share the slides. Yeah.
wonderful? Second question from Isabel: would you consider your model being a digital twin of the water system?
This is a really good question. I mean, I have a mixed feelings about that, to be completely honest. In one way, I mean, and we had an excellent presentation from Professor Mike Batty from the UCL, who is an urban planner and works on digital twins. He was explaining in a great level of detail the definition of a digital twin. And I think fundamentally it will come to that. What do we agree is the definition of the digital twin? Again, twin means, if we say twin is, something that this is the same as the physical environment, then in a way, yes, but then any model is the twin of one part of the system. Where I kind of think we are close to that definition is because I think because we're trying to integrate things, we are slightly closer to the reality, at least for some decisions or some analysis, than if you model different systems individually, or if you just model flow or water quality and so on. One thing that we don't have, which is also linked to the definition of digital twin, is that kind of fully interactive real-time exchange of information, which I think is also how most people see digital twins. I think there is a potential, and we are thinking about that. So if we would have so if the model would be fully online, we have some real data feeding in, and these data inform the change in the operational rules. I think this is probably when the model will be closest to some form of a digital twin. But at the moment, we are not using, I mean, sometimes, I'm not using that term for this model because I don't think that I'm sure exactly what the water digital twins are. So yeah, but it's an excellent question.
Okay, do we have any other questions from the audience? And then we'll go back to the chat. Well, we have a question from Stefano. How do you integrate territorial water to the vertical political decision makers?
So as I mentioned, I work here a lot with the UK Environment Agency. Again, who are, well, they are not, they are the regulator, they're more on kind of implementation of the regulation. But I think where the role of engineers, so again, I am talking about this primarily from the engineering perspective, where the role of engineering is and where we see the value of the model is to, again, design a model that can replicate the system in its entirety is probably kind of very optimistic. But again, to capture as many important elements as possible to represent behavior, the behavior that influences the operation of the system, which then influences the environmental performance, and then have the capability to change that. Okay, so if the regulator is thinking about some new policy, okay, so they're thinking about maybe different abstraction licenses, we can, they can tell us, try this, this, and this, and this, and we give them evidence to see if their policies would work the way how they are envisioned, how they imagine it. Again, we could, also advise to say, well, the model says, try this, not this, the model says you may have these unintended consequences. Will they listen? I have no idea. We do work, Sam mentioned in the beginning, so we do work with social scientists at the UCL. And what we hope to get from the Ventura project that Sam also mentioned. So for the Ventura, what we're doing, we are building the interface. We call it virtual decision room. We are building an interface between the model and the decision makers. And we also are hoping that, so UCL team will be looking into the way how they use that decision, how they use the information to make collaborative decisions. And I think this will give us, again, something to understand a bit more around the influencing this kind of really social science part of that. But you know, from my perspective, I think where we put the boundary of our work is to say we want to you know, build a model that can give you useful information, and we want to try to ensure that the model is, you know, is valid, and then you tell us scenarios. I mean, we can tell you scenarios, but that we are not making the final decision, luckily, or not. I don't know. Maybe if you would have that power, maybe, I don't know.
Let's go to Roger's question about phosphorus. He says that from experience, mechanistic modeling of phosphorus is quite complicated. Does this model incorporate mechanistic modeling?
So for the details of the modeling, I would have to refer you to the papers and the and the PhD students I mean, for any great level of detail. What we did, so for the water quality modeling, we didn't make it up. So we are using the algorithms which are behind the HYPE model. The HYPE model is a low complexity water quality model, which is used a lot in the UK, and we found those algorithms suitable to be linked with other components of the model that we have. And we were also wondering about that as well. I mean, because we are simplifying a lot of things. So we are representing river as a bucket, which maybe hydrologists would now look at me very weirdly and so on. But I think what you have to bear in mind with this type of modeling is, you know, we are sacrificing that level of detail to add all the key, or what we believe are all the key processes that affect dynamics of the different environmental indicators. And what is also interesting, and then we compare that with the observed data, but because the data, at least the data we are using, which are publicly available, are sample data, so there's sometimes kind of once a month, sometimes even less frequently, and that it's just a sample, and we are modeling our simulations are on a daily time scale. So we did do comparison. We haven't published that yet, so but we are looking. I mean, we are working on that. We did the comparison between our model with the INCA model, which is also the water quality model developed by the University of Oxford, which is the digital physically based model of the water quality. And surprisingly or not, we perform comparatively well. I mean, their model is not. I mean, I think water quality models generally are not easy to I mean, or water quality is not easy to simulate. Lots of papers that we were looking at don't, at least the metrics that they communicate compared to different observed data is not. I mean, the flow is much easier to model than water quality. But then again, from everything we've done so far, we are not worse than existing water quality models. So we are like, okay, we can live with that. But I can send the. So we have published the paper on the catchment modeling, so I can send that as well.
And I think we can post those along with your slideshow, so those are available.
Yeah, I can add the references in the slide, so it's all kind of in one place.
Wonderful. So I guess there's a bit of a pause in the chat. Do we have another question from the audience? I'll ask a question. I'm wondering, you started out talking about the environmental capital as the mental model, basically goal. I don't know if you'd call it an objective function, but it's determining your kind of how you're measuring your indicators. And here in New Mexico, our law for water supports beneficial use. So usually that means the benefit is something that ends up, this is way oversimplification, but the benefit ends up in some economic output. So if we wanted to compare mental models or sort of environmental system health versus this beneficial use, would you have it back in your mental model goals, or could you just simulate that with policy on the other end of the model?
That's a really good question. I mean, the way how maybe okay, where to start? Maybe just to say that I am personally a bit a kind of, and I know that's not a good thing, skeptical about trying to, put the value on the environment. But I know this is completely silly because this is how the world works. So, I think, and again, the question is, so what is for me the most difficult question? So the model can tell you what is the, say, water quality, okay, or what is the level of water availability. How do you then translate that? And the model says, okay, it will be a good water quality. How then you translate that into some economic value is really, difficult for me to, I know some economists would probably say, well, this is, very easy. But fundamentally, I think if the environment is used for some business purposes, then it's probably easy because, you get the profit, or if the lake, it's polluted, then people don't come, and then you have loss and so on. On the social side, so kind of appreciation, I have no idea. You can probably model that. You can make some assumptions that if the water quality is good, then more people will come and they will spend more time. But for me, these are all very, how to say, I don't know, too fuzzy assumptions. Although, if they're useful, I'm happy for them to be made. I'm not sure. Again, I'm not social scientist. I know some colleagues have done interesting work around analyzing Twitter data to understand how citizens think or talk about rivers, for example. And then I was wondering, could you use that information to kind of somehow quantify the value of rivers for people? I'm not sure. For me, I think the fact that the river is in a, we could maybe say, that exists, isn't it? The standards of water for, supply, for ecology, for recreational use, and so on. And then if we are achieving that, then there has to be money in a way, almost without trying to monetize, who will make the money out of that. But I know it's a bit idealistic view, but yeah, and it's a long answer to your question.
Intriguing. I think this discussion would be great to continue, but I think I need to turn it back to Ashley.
Thank you, Sam. I think we're right at time. Your presentation was wonderful, Dr. Mijic. It was an honor to have you here today. Before everyone goes, we just put in the chat all of the links to join the TGRR mailing list, Slack, and participate in our survey, and also the volunteer opportunities. But thank you so much, everyone.
Thank you for having me.
Thank you.